Hi, Steve Hughes here, and in this video we're going to look at Lenz's law, which is the physics behind electric power generation. I'm going to do that with this copper tube and a magnet. This is a rare earth magnet. If you've seen the video on the strong nuclear force, it's one of those magnets. Now, before we start, just demonstrate that copper is not magnetic, so it's not actually attaching to the magnet. But if we take steel, for example, so a steel table, and I've got to be careful, you have to be careful with these magnets, they can squish your finger. So I've got to attach there, and this is so strong, I can actually drag this table along, okay, like that. So just how strong this magnet is. Now, another thing I want to demonstrate is dropping the magnet in this perspex tube with exactly the same internal diameter as the copper tube you saw just now. It's about 35 millimeters in diameter. So I'm going to just drop it, sort of 3, 2, 1, and it drops fast. Oh, just like that. Oh, if I get this off. So just do it again. So 3, 2, 1. So it's dropping, basically accelerating under gravity, and there's really no kind of air friction to actually slow it down. Now look what happens when we drop it through this copper tube. So I'll do the 3, 2, 1 again. So 3, 2, 1, go. And I think you can see it's moving very much slower, like that. And we'll have a look at the slow-mo, looking down here, and you'll see it moving down really slowly. This is normal speed video, and this is slow-mo. So the interesting question is, what is slowing the magnet down? What is sort of producing that kind of extra kind of viscosity, like a magnetic viscosity, as it goes down? Now, I want you to imagine being inside this magnet with a magnetometer to measure the magnetic field strength. And so the magnet gets pushed in, and we're there. We see this sort of magnet coming down towards us, kind of a dark shadow. And as it gets closer to us, the magnetic field strength goes up, reaches the maximum. It's flat as the magnet passes us, and then it goes down. And that's key to understanding what is going on here. Now, as the magnetic field strength goes up, as it comes down, that induces an electric current in the surface of the copper tube that goes in the direction of my fingers. Actually, it's electrons going the other way, but it's positive current going in the direction of my fingers, and current going around like that. So as we look down, going anti-clockwise, produces a north pole in the direction of my thumb, okay? And so as the magnet falls down, it causes current to go round in a circle, inducing a virtual magnetic north pole in front of that, if it is the north pole coming down. If it's a south pole, it'll be a south pole in front of it. So it's got this kind of a drag in front of it, or a magnetic cushion as it comes down. Now, on the other side of the magnet, where the magnetic field is going down, then it's going to be the opposite. We just sort of flip around like that, so the current goes that way, and this time we've got a north pole pointing down like that. And that actually drags on the south pole on the other side of the magnet. Assuming it's a north pole on the front, there must be a south pole on the rear. And so we've got a magnetic cushion in front of the magnet and a kind of a magnetic drag effect on the rear of the magnet. So that's what is slowing it down. Now, Lenz's law has got a negative sign in front of it, which indicates that when a magnet falls down in a copper tube, for example, the current goes in a direction that it produces an opposing magnetic field. Now, when we think about it, nature has actually got to be that way. Suppose for the moment that Lenz's law didn't have that negative sign. So what would happen, I would sort of push this magnet into the copper tube, assume it's the North Pole going in first, and what would happen, as I pushed the magnet in, it would produce a South Pole in front of the magnet, and that would actually attract the magnet forwards. On the other side, where we've got a South Pole, there would be an opposing South Pole which would push on it. So in principle, we could construct a long copper tube pointing at the moon, poke the magnet in, and it would just shoot out at enormous speed, going fast enough, you know, greater than the escape velocity of the Earth. We'd actually hit the moon, a bit like the Jules Verne movie, where people get put into a capsule which is fired to the moon. In principle, we could actually do that. But the question is, where would the energy come from? That would be a violation of conservation of energy. And so by looking at that, we can see there's got to be that negative sign in Lenz's law. So here's just a diagram explaining what's going on. We've got the falling magnet there with a North Pole there and a South Pole and the green magnetic field lines. And so as the magnet falls down, we've got a region of increasing field strength here. That produces an opposing North Pole with the current going around like that, producing an opposing North Pole. And then behind, where we've got a reducing magnetic field strength, we get an opposing South Pole. It's got the current going in the opposite direction of what we've got down there, and that actually pulls on this end of the magnet. So that's what actually slows a magnet down as it falls in a copper tube. And also it does illustrate the physics behind electric power generation. We've got a moving magnet producing a moving current. So basically, that's what happens in any sort of power station. It's magnets moving in relation to wires, which produces an EMF, electromotive force, or a force that moves electrons.